Okay, so this video is going to be over Energy 1A, which has to do with work and power, both the concept of work and the equation, and then we'll be doing calculations with power. Just like normal, you should take good notes as we go through this PowerPoint. I will definitely link the PowerPoint so you can access it on your own, and you can always access this video on YouTube because there's a link to my YouTube playlist posted at the top of the module page on Canvas. Okay, so let's start by talking a little bit about energy. Now, in your previous science class, you've probably heard about energy before, and you've probably talked about different types of energy. Okay, so what are some different types of energy that you can think of? Now, just to name a few that you might have heard of, okay, we have kinetic energy, potential energy, mechanical, electrical, and this is not a comprehensive list. Okay, this is just some that are kind of occurring to me off the top of my head. We have chemical energy, we have hydroelectric energy, wind, solar. There's lots of different energies we could come up with. Now, the primary types of energy that we're going to focus on, at least in this unit, are the first three. Kinetic energy and potential energy are both two very common types of energies. And mechanical energy, as we'll see, is actually the combination of kinetic energy and potential energy. Okay, so the other energies, and again, this is not a comprehensive list. You could easily come up with more, but these are just ones that occur to me. The other types of energies are important, but they won't be showing up too much in this unit. Now, we talked about different types of energy. I haven't told you what energy is, and I can't really tell you what energy is because it's a very abstract type of thing. And I know it's not good to tell you that we don't know what something is, but we don't really know what energy is. We know a lot of things about energy, and we know its properties. We know it's something that can be measured and calculated, but actually putting a definition on the concept of energy is not so easy to do. So a common definition that you might hear for energy is the ability to do work. Now the problem with that is that definition is that in just a couple minutes I'm going to define work as basically the transfer of energy to or from an object. Okay, and so defining energy in terms of work is not really useful since we're also going to define work in terms of energy, and so I haven't really told you anything with that definition. Okay, but I can tell you some things about energy. I can tell you that there's different types of energy, that objects can possess different types of energy in different forms, and that energy can change from one type to another type. But as far as we know, in all of the universe, energy cannot be created or destroyed. It can only change from one form to another form. And this is a really important concept. This is called the conservation of energy. It's one of the fundamental principles of mechanics and also of physics in general. So I will link this simulation so you can check it out on your own, basically just seeing how energy can change from one form to another form. Okay, so I haven't told you what energy is, but I told you a little bit about energy. Okay, so let me tell you a little bit more about energy. The symbol for energy that we will use is going to be a capital E. Okay, not to be confused with a lowercase e, of course. Now, we're going to use subscripts to denote different types of energy. And we did this in the first semester, we did this with forces. Now, what I mean by subscripts to indicate the type of energy is, for example, for mechanical energy, we write E mech. Or for kinetic energy, we might write EK. Or for, I don't know, thermal energy, we might write E thermal. And so capital E is the symbol for energy, but then we can use subscripts to denote different types of energy. Now, the unit for all types of energy is the joule. Okay, just like the unit for all types of forces is the Newton, the unit for energy is the joule. Now it's a capital J because it's named after a physicist whose name was Joule, which is why it's capitalized. And that is the SI unit for energy that we're going to be using in this class. And so when we do energy calculations, all of our answers are going to be in joules. Now there's different units for energy that we're not going to worry about in this class. but when you go up to higher levels of physics, you do talk about different units of energy. One unit of energy that you might be more familiar with that we're not going to see in this class, but it is a unit of energy, is the calorie. And so you typically see calories when you talk about food. Okay, so for example, if I eat something that's worth 100 calories, a calorie is a unit of energy. Okay, 1 calorie is equal to 4,184 joules, and we're not going to get into why it is, that has that conversion factor, but that's another form of energy. Okay, so I said before in this unit we're going to be focusing on mechanical energy, which includes potential energy and kinetic energy. Now, before we get to those types of energies, we're going to start with the basics, and we're going to start off by talking about work and power. Okay, so pause there if you need to write any of that down. Okay, so let's talk about work. Okay, now, in physics, to do work basically refers to the ability to transfer energy to or from an object. Okay, so it's not like, you wake up and you go to work. Work is something that is done on an object. Okay, so this is the concept of work. It's really important that you understand the concept of work, because concepts are really important in this unit. You can't just do calculations without understanding why you're doing the calculations that you're doing, or why the calculations make sense. So you need to know the concept of work. Okay, work refers to the transfer of energy to an object. So for example, when I kick a football, I transfer energy to the football. It goes from my body to the football. I would say that I do work on the football, because the football gains energy from me. Energy was transferred from my body to the football. Now, where did I get my energy from? From the chemical energy in the food that I eat in the morning. Okay, when you push a chair, right, you do work on the chair. You transfer energy to the chair, and then it rolls across the floor. When your car coasts to a stop, let's say you're driving along, you run out of gas. Okay, your car is eventually going to slow down and stop because of friction. Okay, in that case, work is being done because friction, the force of friction, is actually transferring energy away from the car into the ground. Okay, so work can also transfer energy out of an object. Typically, we talk about the work being done by a specific force. So in that last example, I would say that the force of friction does work on the car to make it stop. When you push on the chair, I would say my applied force, when I push on the chair, does work on the chair. Okay, so again, understand the concept of work as the transfer of energy to or from an object. Okay, now with that being said, in just a moment we'll be doing calculations with work, but you also need to understand the concept as well. Okay, pause there if you need to look at that. Okay, so let's move on. Okay, so recall that work is done by force when energy is transferred to or from an object. We talked about that on the last slide. Now, here is the equation for work. Okay, for work, we write a capital W. Okay, capital W for work. And to calculate the work done by a force, we take the size of that force, which is capital F, and we multiply by d, which is the distance that the object moves. Okay, so force times distance equals work. Okay, now don't forget that units are important to know. Remember that the unit for distance is measured in meters. Okay, we saw that in the last semester. Force is measured in newtons. That's, how big your push or pull is. And then work. So work is not energy, but work is the transfer of energy. Okay, and so work is measured in joules. And so the unit for work is also joules. And so all energy plus work is measured in joules. Now, what factors influence work? Well, if you look at the equation, obviously the two factors that matter are the force and the distance. If you push with a harder force, you do more work. If you push an object over a bigger distance, you do more work. Okay? So those are the two factors that influence work. Now, work can actually be positive or negative. So what is meant by positive work? And this might be kind of a common sense type of thing, but remember that the concept of work is you're transferring energy to or from an object. So what is meant by positive work? Okay, positive work means you're adding energy to an object. Negative work means you are removing energy from an object. And that's, again, probably like a common sense type of thing. Positive you think of adding, negative you think of subtracting. Okay, so keep in mind work can be positive or negative. Pause it there if you need to write that down, and we'll do some examples. Okay, so example 1. It says a woman pushes a shopping cart at a distance of 16 meters. Right off the bat, I'm going to identify that as one of my given pieces of information. I'm going to label that D. That's the distance that the shopping cart moves, with a force of 20 N. Remember, N is newtons, because force is measured in newtons. Okay, so I'm going to label that with a capital F for force. Now the question says calculate the work done by the woman. So we're just going to use the equation for work, and this is a very simple calculation. Force times distance. The force is 20. The distance the shopping cart moves is 16. And so if you plug that into your calculator, you get 320 joules of work. Now, the second question is a concept question. Is this positive or negative work? So remember, positive work, energy is being added. Negative work, energy is being removed. Okay, so you have to think, is the woman adding energy or taking energy away when she pushes the shopping cart? Well, she's probably adding energy. So I would say that this is positive work. Okay, because she's putting energy from her body into the shopping cart. Okay, so that is example 1. Please pause it there if you need to take a look at that. Okay, so example 2. It says a car traveling down the road with 500 joules of kinetic energy stops over a distance of 25 meters. Now, we've got an energy, but remember, we haven't even talked about energy yet. This is 500 joules of kinetic energy, but we haven't talked about that yet. We do have a distance, so I'm going to label that D. The first question says calculate the force. So we're looking for force, that's our unknown, that acts on the car to make it stop. Now this is completely a concept question. Okay, you need to understand the concept of work. Because remember, work is the energy added or removed from an object by a force. So if we want to make the car stop, if it starts with 500 joules of energy, and we want to make it stop, how much of that energy do we need to take away? Okay, well, if we want to make it stop, that means we need to take all of the energy away. So that means we need to do negative 500 joules of work. Okay, because it has all that energy and we want to take that energy away so the car stops. Now, as long as you can figure that out, then all you have to do is use the equation for work to find the force, negative 500. We leave F in the equation because that's the unknown. D, the distance is 25 meters. Because 25 is multiplying F, I want to undo that multiplication, so I'm going to divide both sides by 25. Okay, and I find that the force is going to be negative 20 newtons. That is the answer to the question. Notice that the force is negative because it's a stopping force. Okay, and the work is also negative because energy is being removed from the car. So pause it there if you need to look at that. Okay. This chart just kind of summarizes what we talked about as far as work goes, positive work, negative work. One more thing you need to know, and I would definitely add this to your notes, is if you look at the bottom, basically you can have positive work, negative work, or zero work. Okay, now it is possible for a force to do no work on an object. You don't need to know about number 1 for this class, okay, but you do need to know about number 2. Basically, you need to know that zero work is done if the object does not move, if the distance is 0. Now, you could probably figure that out because work is force times distance, and so if the distance is 0, 0 times anything is 0, so that might make sense in your head anyway. Okay, but if an object does not move, that means there's no work being done. That means there's no change in energy either to or from the object. Okay, so keep that in mind. Pause it there if you need to look at that. Let's do another quick example. Okay, example 3, in which of the following examples is work being done? Okay, so we have either a box is set on a table and does not move, a weightlifter holds a barbell motionless above their head, a man pushes a shopping cart in the store, and a car sits at rest on a steep hill with the parking brake on. So remember in the last slide we talked about how work is only done if there's a distance, if the object is moving. And if there's no motion, that means there's no distance, that means the work done is 0. Okay, so the only situation of these 4 where work is being done would be this one right here. Because in all the other situations the object is not moving. Okay, therefore no work is being done. The work done is equal to 0. Okay, so pause there if you need to look at that. So moving on. One more thing you need to know. You sometimes see problems where you need to lift an object up. Here's something really important that you need to know. In order to lift an object, the force required to lift the object must equal the weight of the object. Now remember, when we talk about weight, we're talking about force of gravity. In the first semester, we saw the equation for the force of gravity is this. Fg, which is the weight, the force of gravity, is equal to the mass times g, where g is the acceleration due to gravity, and on Earth we use a value of -10 meters per second squared. Now, in this unit, we are going to use a positive 10 for this force. Okay, we're using a positive 10 because with energy the direction doesn't matter. Alright, and so please keep in mind, in order to lift something up, the force you have to apply is equal to the weight of the object in newtons. Okay, so if you're given the mass in kilograms and you're lifting the object up, you need to convert that mass to force by multiplying by 10, basically. Okay, so quick example, pause it there if you need to write that down. Okay, example 4. It says a man lifted a 120 kilogram. Notice kilogram is the unit for mass. Okay, so this is the mass. He's lifting a barbell up off the ground a distance of 0.2 meters. So I'm going to label that D. Notice I'm not actually given a force, but I am asked to calculate the work. Okay, so when I go to use the work equation, that's force times distance, I'm not given a force. But remember, to lift something, right, the force you have to apply is equal to the weight, the force of gravity. Okay, so the force I need to apply, I'm going to take that mass, 120 kilograms, multiplied by g, which again we're using a positive 10 because the direction doesn't matter. Okay, so to lift the 120 kilogram barbell, I need to apply a force of 1200 newtons. And so there's my force. I have 1200 times the distance of 0.2. That's going to equal 240 joules of work. Okay, and that's how much energy the weightlifter transfers to the barbell when he lifts it up. Okay, 240 joules of work. Definitely pause it there, check the answer for yourself, make sure that you get the same answer. Make sure you understand that when you see mass, to get the force, you need to multiply by 10 to convert from mass to weight. Alright, so I'm going to erase this, pause it there if you need to finish copying that down. And the last thing we're going to talk about in this video is power. Okay, so very quickly, power is related to work and energy. And basically, power is the rate that energy is used, or the rate at which work is done. So in other words, it's not just about energy, but it's energy over time. How quickly can that energy be used? So, some facts about power. The symbol for power is a capital P. The unit for power is the watt. Now, confusingly, watt starts with the letter W, so we also write W for watt. That's a little confusing because we also write W for work. So you can tell which one is which based off of the context. If I say W equals 5 joules, that means this W is work. If I say P equals 10W, if it comes after a number, that means it's a unit. This would be, the power is 10 watts. Okay, so sorry for that confusion. Now, what is the equation for power? Well, the equation for power is this. Power equals W, remember W is work, divided by time. Okay, so work over time. Again, how quickly is the work being done over time? Now, 1 watt is equal to 1 joule per second. Okay, so 10 watts means something is using 10 joules of energy per second. If you buy a 40-watt light bulb at the store, that means it uses up 40 joules of energy every second. Okay, so work has to do with how much energy is transferred to or from an object. Power tells you how quickly that energy is transferred to or from an object. Okay, so pause it there. Make sure you have the equation for work and the equation for power in your notes. Okay, and then we will do a couple examples before we finish this video. Okay, so example 5 says calculate the energy in joules that a 60-watt light bulb. Notice I know this is watts because it comes after a number. Okay, so this is power. 60-watt light bulb and a 100-watt light bulb emit in 30 seconds. Okay, so I'm just going to do this really quickly. Remember, power is work over time. And so 60 watts is the power. Okay, so if I plug in 60 for power, and I want to know how much energy is transferred, I plug in 30 seconds. Notice if I'm looking for work, and I'm dividing by 30, I need to multiply by 30 on both sides to undo that division. And so 30 times 60 is 1800 joules, and that's 1800 joules of energy. Now, what about the 100-watt light bulb? Well, see if you can do that on your own. Okay, so pause it there and see if you can get this answer. The 100-watt light bulb would be 3000 joules. Okay, again, 100 watts is 100 joules per second. Okay, so you would multiply by the seconds. Pause it there if you need to look at that. We'll just do a few more quick examples with power. Okay, example 6. Two weightlifters, Sam and Cam, each lift their respective weights as quickly as they can. Sam lifts his 100-kilogram barbell a distance of 0.35 meters in 0.4 seconds. Cam lifts his barbell over a distance of 0.5 meters in 1.2 seconds. Now, this is a full-on example, so we're going to stop after this one. If you want to try example 7 on your own, you're welcome to do so. Okay, but let's do this example. Okay, so first, let's identify the given information. Alright, so Sam, we have the mass of the barbell, not the force, not the weight, but the mass in kilograms. We have the distance, and we have the time. So for Sam, to calculate the work, first I need to find the force, which is the force of gravity. And the force of gravity for Sam's barbell would be mg, that would be 100 times 10, which would be 1000 newtons. Okay, so for Sam, his work would be equal to 1000, not 100, 1000 times the distance of 0.35. Okay, so Sam, when he lifts his barbell up, does work equal to 350 joules. Okay, that's for Sam. Now for Cam, I do something very, very similar. Notice I have the mass of Cam's barbell, 120, and I have the distance. Okay, again, I need to use the weight equation to calculate from kilograms to newtons. Okay, so 120 times 10 is 1200 newtons of force. So Cam's work would be force times distance, which would be 1200 newtons times the distance of 0.5 meters, and that would be 600 joules. Okay, so which one does more work in lifting their barbell? Well, clearly that would be Cam, because he's lifting a heavier barbell over a bigger distance. Okay, 600 is bigger than 350. Alright, that answers the first question for example 6. Now, which one exerts more power? Remember, power is work over time. So, for Sam, his work of 350 divided by his time of 0.4 seconds. Okay, if you do 350 divided by 0.4, you get 875 watts. Okay, if you do the same thing for Cam, again, power is work over time. 600 divided by 1.2, you get 500 watts. And so Cam might be stronger, he might be able to lift a heavier weight, but he is not more powerful. Okay, because Sam can lift his smaller weight in a third of the time as compared to Cam. Okay, so I know that was a lot of information. Definitely go through the notes on your own. Try to do example 7 if you can. Please let me know if you have any questions, especially on the practice worksheet. Definitely let me know if you have any questions before the quiz. Remember, you can repeat the practice assignments as many times as you want, but the quiz you can only do one time. So please reach out to me if you have any questions. And as always, I will see you guys in the next video.